Hello everyone, we are Team 1038 from Karazin Kharkiv National University, and today we are excited to present our project titled It is Raining Space Dust. Here is what we will cover today. We will start with an introduction to the problem, then move on to our mathematical model and the numerical approach we used to solve it. After that, we will analyze our results and finally discuss how we can estimate the initial dust distribution from surface data. Cosmic dust is constantly entering Earth's atmosphere. These particles range in size from about 1 to 1,000 micrometers and originate from comets, asteroids, and other bodies in the solar system. Studying this dust is important because it helps us understand the early formation of the solar system and the physical and chemical processes occurring in our atmosphere today. In our research, we focused on two main questions. First, how does atmospheric entry influence the physical and dynamical properties of cosmic dust? And second, is it possible to reconstruct the initial distribution of these particles based on what we find on the surface? These two questions guided our entire study. Our goals were to model the behavior of particles during atmospheric entry, predict their outcomes under different initial conditions, and explore whether the initial distribution can be estimated from the characteristics of the particles that reach Earth's surface. In our model, we considered the main physical effects acting on a particle. It experiences gravitational force pulling it toward Earth and atmospheric drag which resists its motion. As the particle enters the atmosphere, it heats up dramatically, leading to ablation, the gradual loss of mass through vaporization. To make our model realistic yet computationally feasible, we introduced several simplifying assumptions. We assume that particles are spherical, that the atmosphere follows an exponential density model, and that ablation can be approximated without detailed temperature tracking. We also neglect wind effects and fragmentation in this version of the model. I will now hand it over to my colleague who will present the mathematical formulation of our model.
Thank you. Our model is described by a system of coupled differential equations. We track the change in x and y coordinates, the change in velocity components, and most importantly, the change in the particle's mass due to ablation, which is dependent on air density and the cube of the velocity. This slide shows our key parameters. We use standard value for gravity and sea level air density. A particle density corresponding to the lost city meteorite and an ablation coefficient from the literature. We tested a wide range of initial velocities and radii. To solve this system, we chose the Runge-Kutta first-order method, or RK45. This method provides the best balance of accuracy and computational efficiency for this system. Especially with the stiff atmospheric density gradients, the simulation stops when the particle hits the ground or is completely ablated. Our algorithm initializes the particle's parameters, solves the ODE system, and at each step it checks the ablation conditions, updating the mass and radius until a final state is reached. Now for the results. On this graph, you can clearly see that initial velocity is the main driver of ablation. A 100 micron particle entering at 12 km per second survives. The same particle at 25 km per second is completely destroyed. The size is also critical. As the graphs show, a 5 micron particle is destroyed almost instantly. Meanwhile, a 50 micron particle penetrates deep into the atmosphere and survives with minimal mass loss. And finally, the entry angle. Counterintuitively, shallower entry angles like 30 degrees are more destructive. This is because the particle spends a longer time in the atmosphere, undergoing a slow roast effect, which leads to greater total ablation compared to the a flash fry of steep entry. I will now pass the floor to Oleksii for the analysis and conclusions.
Thank you. My colleagues showed the effect of each parameter individually. We combined them into this particle map. This heat map showed the final radius of every particle on the ground. We can clearly see the zones. Dark areas represent complete vaporizations where particles are small and fast. The bright areas are survival zone for large and slow particles. This survival map explains what we see here. On the left is the hypothetical uniform distribution of particles in space before. On the right is what we get on Earth after. The atmosphere acts like a non-linear filter, selecting and destroying small, fast particles, which squeeze the surface distribution to the right. Now we can answer our main questions. Question 1. What happens to particles? Our Ford model successfully predicts their state, where we see the many particles irretrievable lost due to complete ablation. Question 2. Can it work backward? Our answer is yes, with caveats. This is the ill-posed inverse problem because the information about vaporized particles is lost. However, using regularization methods, it is solvable. Its accuracy depends heavily on the quality of surface measurements. We assess our model as follows. Its strengths: it is physically based and computationally efficient. Its limitations: we assume spherical particles and did not include fragmentation. In future work, we plan to incorporate rotation, stochastic fragmentation, and chemical composition. In conclusion, our model successfully predicts particle behavior and identifies the critical criteria of survival. We have demonstrated that solving the inverse problem to estimate the initial distribution is feasible. Our practical recommendation is that for ROPS reconstruction, we must combine multiple data sources, surface collection, radar observation, and satellite data. Here is the primary reference we used for our work. We are grateful to our coach Nataliya Goncharuk, our school and university teachers, and the organizers of SCUDEM. Glory to Ukraine!